Welcome to our discussion about logarithmic functions and their corresponding equations. And in this video, we are going to focus on how do we graph logarithmic functions. So let's jump in. We're going to start like we did with exponential functions and really just kind of talk about the graphs of the parent function y is equal to log base b of x. So if you notice to the right here, I have actually two graphs. The graph in blue is the exponential function, y is equal to 2 raised to the x, while the graph in red is y is equal to log base 2 of x. Okay, they are inverse functions, okay, and that's the reason why I've got them both on the graph. We're going to focus on this red graph, the log function, and I want you to understand that this is the same as x is equal to 2 raised to the y. Okay, and so the reason why I've got both of those there is because remember that when we talked about inverse functions, the domain of a function is the same as the range of its inverse, and the range of a function is the same as the domain of its inverse. And so I wanted you to kind of see that relationship here. But what we are really looking at here is the red graph. The blue is just for reference. Okay, so let's look at this red graph. Y is equal to the log base 2 of x. Notice that we have this curve, and instead of approaching the negative x-axis, this is approaching the negative y-axis, okay, and it does not extend beyond the y-axis at all. And so our domain here is going to be from 0 to infinity. And you might remember that that is the range of this exponential function. You can kind of see that here, right? This graph does not extend below the x-axis, it just goes up from there. Now the range of the red function, notice that it goes infinitely down towards negative infinity, and it goes infinitely up towards positive infinity. And so this range is going to be negative to positive infinity. It's the same as the domain of the exponential function. Oh, the horizontal asymptote, there isn't one. So let's fix that right now. Okay, the vertical asymptote. As you can see, this graph has, instead of a horizontal asymptote in blue, it has a red vertical asymptote. And it behaves a lot like what we saw with the exponential, but it's vertical. This graph is going to run right alongside that x value. So our vertical asymptote is going to be x equals 0. Now, if you can look at this, you can see that in this case, we definitely have an x-intercept. You can see where this is going to cross the x-axis at the value 1. And there is not a y-intercept because it just runs directly down that y-axis. So there is not one here. And similar to exponentials, if the base of the log function is greater than 1, our graph is going to be strictly increasing. That means the entire graph will be increasing from left to right. And if that base is between 0 and 1, our graph will be strictly decreasing. Okay, so let's look at a couple of examples of graphing logarithmic functions. All right, so we are going to take a look at this function. Y is equal to log base 2 of the quantity x minus 3. Okay, and what we're going to do is we're going to create a table of values, plot the points, sketch the curve, and then analyze the graph. Now notice that our parent function was y is equal to log base 2 of x. So if we're taking the log base 2 of x minus 3, we think that this has shifted our parent function 3 units to the right, knowing what we know about transformations. Okay, so how do I graph this if I didn't really know how to use a graphing calculator or I wasn't allowed to? what you're going to do is rewrite this in exponential form, okay? So let's take this and rewrite this in exponential form. Let's remember that this is the same thing as 2 raised to the y equals x minus 3. And then I can just solve for x and say, well, that means x is equal to 2 to the y plus 3. So we can, instead of putting values in our x column, we're going to put them in our y column and then evaluate the x column. So we're going to use this equation, x is equal to 2 to the y plus 3, and we're going to substitute in negative 2 for the y. So 2 to the negative 2 is 1/4, plus 3 is going to be 3 1/4, otherwise known as 13/4. 2 to the negative 1 is 1/2, plus 3 is 3 1/2, otherwise known as 7/2. 2 to the 0 is 1, add that to 3, we'll get 4. 2 to the first is 2, plus 3 is 5, and 2 squared is 4, plus 3 is 7. So we have a nice table of values that we can use then to plot some points. So let's plot those points, and we can see that logarithmic curve starting to emerge, right? Okay, now we will want to definitely sketch the asymptote, right? And the asymptote is going to be found when we take the argument of the log and set it equal to 0, okay? Remember, you can't take a log of something that equals 0. And so if we take that, we can find the location of our asymptote. So our asymptote is going to be at x equals 3, right? And then we can sketch the curve that goes with this log function. There we go. Okay, and so now we've got a graph that we can look at and analyze. So here is the graph analysis. Let's take a look at all of these things and see if we can figure them out from this graph. Okay, how about the domain of this function? How far to the left and how far to the right does this function go? Notice it comes along that asymptote, so it's not going to go any further to the left than this x value of 3. So the domain here is going to be from 3 to infinity. Our range is going negative to infinity to positive infinity. And our vertical asymptote, as we said before, is x equals 3. We have an x-intercept, can you see it, at 4. There is no y-intercept. There is no relative max or min because this graph is strictly increasing, and a relative max or min would occur when there's a change from increasing to decreasing or vice versa. So what is the interval of increase? Okay, so this is a little bit trickier because we need to think about where is this function increasing. And you could definitely say it is increasing everywhere the function is defined, but it's not defined everywhere. We're going to go back and say that the interval of increase is the domain of the function because everywhere it's defined is increasing. And where is this function decreasing? What's the interval of decrease? It's not decreasing, so we'll say none there. Now, where is this function greater than 0? Now this, you want to think about the domain of the part of the function that is above the x-axis. Okay, so think about from here over, what is the domain there? Okay, we can say that that is from 4 to infinity. And where is f of x less than 0? That will be the domain of the function where it's below the x-axis. So notice it's just this little bit. From positive 3 to positive 4 is the domain of where it's below the x-axis. So from 3 to 4. Okay, that wasn't too bad. Let's try another example of graphs. Okay, for this one, we've got the function y is equal to log base 2 of x plus 1. Now notice, what are we taking a log of here? We're not taking a log of x plus 1. We're taking a log of x because that plus 1 is not in the argument of the log. Okay, so what is that plus 1 doing to that log base 2 of x? Well, based on your knowledge of transformations, that plus 1 is shifting that graph up 1 unit. Okay, so this is what we should be expecting when we graph this function. Let's take a look. Let's go ahead and then rewrite this in exponential form. Now we can't actually rewrite it in exponential form until that log is isolated. So the first thing we're going to do is move this 1 to the other side and say that this is y minus 1 is equal to log base 2 of x. And now we can write it in exponential form. 2 raised to the y minus 1 is equal to x. All right, so here is what we're going to use to fill in our table. We're going to go ahead and use those y values, -2 to +2, and sub them in. So when I sub in -2 here, I've got 2 to the -2 minus 1, or 2 to the -3, and that will be 1/8. And then if I sub the -1 in, 2 to the -1 minus 1, or 2 to the -2, which is 1/4. And if I sub in the 0, I've got 2 to the -1, which is 1/2. And when I sub in the 1, I've got 2 to the 1 minus 1, or 2 to the 0, which is 1. And last, 2 to the 2 minus 1 is 2 to the first, which is 2. Okay, so I've got some nice points that I can plot. And when I plot them, it kind of looks like this. All right. And can you tell me what the vertical asymptote is going to be? What are you taking the log of? Now set that equal to 0. So our asymptote is going to be x equals 0. Okay. And so you can see that vertical asymptote here. And when we sketch the curve, we've got that nice logarithmic function happening. Now let's take a minute and use this graph to analyze the function. All right, take a look at this. Tell me about the domain. What do you think about the domain here? The domain doesn't go any further to the left than this asymptote, right? So our domain is going to be from 0 to infinity. The range is -infinity to +infinity because this graph goes infinitely down and infinitely up. Okay, vertical asymptote we said was x equals 0. The x-intercept is 1/2, and there is no y-intercept. Again, there's no relative max or min because this is a strictly increasing graph. What is the interval of increase? Where is this function increasing? Okay, and so as we said before, that would be everywhere it's defined, which is going to be what we have classified as the domain. So our interval of increase here is 0 to infinity. And then the interval of decrease, there is none because this is a strictly increasing graph. Where is this function greater than 0? Well, that's everywhere, or the domain of the part of the function that is above the x-axis, okay? And so just focusing on this part, what's our domain? And that's going to be from 1/2 to infinity. And then where is a function less than 0? Again, that's asking you to look at where is this function below the x-axis. So if I'm focusing on this portion of the graph, what is the domain here? And that's going from 0 all the way to 1/2, and that's our domain. And so that gives us a nice graph analysis. We've got one more example of graphs of logarithmic functions, and let's take a look at that. This graph is going to be the graph of the function y equals negative log base 2 of x. All right, so what do you think? With our parent function of log base 2 of x, what do you think is going to happen with negative log base 2 of x? And if you said that this looks like a reflection over the x-axis, you'd be right. So we should see that entire graph kind of flip upside down when we're done. All right, so let's go ahead and rewrite this in exponential form so that we can fill in this table of values. Now remember, this log function needs to be isolated before I can write it in exponential form. So I need to move this negative to the other side. I need to divide by -1, and I would get negative y is equal to log base 2 of x. And now I can rewrite that in exponential form. 2 to the negative y is equal to x. Okay, so now I can use those y values of -2 to 2, and I can sub in that -2 here. If I put a -2 in for negative y, that will become a positive 2, so 2 squared would be 4. Again, if I put a -1 in here, -1 would be +1, and 2 to the first is 2. 2 to the 0 is 1. 2 to the -1 is 1/2, and 2 to the -2 is 1/4. Oh, that doesn't look like what I've seen before. Okay, but remember we said that we thought this was going to flip our function over. All right, what's that vertical asymptote? Set the argument equal to 0 to find that, and we can say the vertical asymptote is x equals 0, and there we go. We have our vertical asymptote of x equals 0. We've got our curve. It is a reflection of our graph of y is equal to log base 2 of x. All right, so let's go ahead and analyze it. Okay, before I go through this graph analysis, I want you to try. Go ahead and try filling these things in and see if you have these concepts down. And then we'll talk about them in just a second. Pause the video and come on back. All right, welcome back. And let's talk about the domain here. The domain here, notice that this graph does not go any further to the left than 0. So our domain is going to be from 0 to infinity. Our range, we have a graph that is going infinitely down and infinitely up. So our range is negative to positive infinity. We have a vertical asymptote at x equals 0, an x-intercept at 1, no y-intercept, no relative maximum because it is a strictly decreasing graph. The interval of increase does not exist. And the interval of decrease is going to be the entire domain of this function, which will be 0 to infinity. Now, where is this function greater than 0? That's the domain of the portion of the graph that is above the x-axis. So we're focusing on this little piece right here. So that domain is going to be from 0 to 1. And then where is a function less than 0? That's everything that is below the x-axis. So that's going to be the domain of this portion of the graph, which is going to be from 1 to infinity. Okay, so that wraps up our discussion about the graphs of logarithmic functions. And in our next video, we're going to be talking about how to solve logarithmic equations using the definition of the logarithm. All right, I'll see you then.